Okay. Start the recording. Oh, sorry. Let me just check everything. Okay, looks good. You made it. Good job. So I'm very proud of you from quiz 3. So good job. It was a very, very good quiz. Now we're going to settle down and do inference for the rest of the term. I feel like snow really messed with me. So next couple of chapters, okay, we're going to do inference for proportions, a single proportion, 2 proportions, right? And then two-way tables, kind of really stepping things up a little bit. But first, maybe let me move this here. Marnie, you can look for your quiz in there. Oops. Inference is hypothesis testing and confidence intervals, right? Kind of an umbrella term for hypothesis testing and confidence intervals, and proportions, two-way tables. I'll add of proportions. Okay. Morning. And then we'll have quiz 4. Really, really condensed, really nice and tight. But there's a lot of stuff on there, right? And so inference, right? For one proportion, we're going to introduce that today. Okay. And then we compare 2 proportions the following day, which is, I guess, Tuesday. And then two-way tables, Thursday. And then quiz 4 the following Tuesday. It's happening so fast now. I know. Yeah, I know. So I know I just finished marking these. I'm going to have to mark more. I know, poor me. So here we're going to have quiz number 4. Now, I was trying to think of cute examples from maybe water engineering that would involve proportions. And I am drawing a blank. I can't think of anything. So I put it out to you. Well, let's bring it back. What do proportions? So we analyze proportions. They're for categorical data. Right? If you think about data that you'd collect, what's a categorical variable? And for today, I've got specifications. Ideally, a yes/no variable, or something that you could turn into a yes/no variable. I feel like you had an idea. No?
Days of, like, say, a week or a month that you're out of compliance, like what we are back.
Okay. So in compliance, out of compliance?
Yeah.
Can we do that?
Oh, I got one. There's annual, you're allowed a certain proportion of annual untreated flow at a treatment plant.
Okay. Okay. Annual unseeded flow. Unseeded flow, yes, no? Untreated.
Yeah.
Okay. Okay.
I think it's 5%.
Let's try untreated flow. Yes, no. Yeah?
Not really yes, no. percentage of your total flow is allowed to be untreated under like your belt.
Is it per day?
Well, sure.
Would-
Or if it's total annual, so per day, sure. It's
So each day could be yes and then no.
not really.
No.
Are you treating or not treating? Yeah, but more important.
Untreated flow.
One of your nodes are less than 5% of your total number of answers.
I mean, yeah, it doesn't work.
Yeah.
How about we pretend it works like that?
You can pretend what-
Because
Where's the wastewater people? What do you do? Portion of your fucking bugs that you recycle or something. Yeah, where's the waste people?
It's just the yes no thing. That's right. Portion of your flow rate and cycle back to like tanks.
I was okay.
Like, yes, no, are you in your permit or without a permit?
And then the follow-up would be, we want to compare it to some number. Do you have an idea of what that number would be then?
Yes, or no's. At the end, you want a percentage of that yeses or no's throughout the entire time period, right?
Yeah.
Yeah.
How about this? We're just going to go for it. I'll stick with the trade because we said it, right? And let's pretend it makes sense, right? But it's a good exercise to think about, what would categorical data look like in our case, okay? And so, and I should have made it the bonus question on the quiz, hindsight 2020, because then I would have numerical variables and categorical variables from you guys, and then I would have to study up. Because what's the next part? The last part of the course is for numerical data, probably more of a moneymaker for us, right? Especially in terms of measurements and the average measurements and comparing averages, right? And so, but we start with proportions, mostly because we just learned about the Z distribution, right? And so we're going to be able to piggyback on that still. And so that's why it's a nice kind of transition. Okay, but buckle up. We will be doing numerical data. Okay. Of course, but not until later. I am going to cut chapter 2 and I'm gonna do something different for chapter 23. Wow. That gives us time to have quiz 4 during the entire class time again. Okay. And also accreditation doesn't need you to be able to compare many means. And at that point, you'll be ready to fly on your own, right? You can do it on your own. I'll post it as a bonus assignment. How about that? You can boost your grades. Then you can study it up or study on it if you want, or ignore it completely. It's up to you. So look at that. That's bite size. We're basically in summer, if you can believe that.
No.
No. Okay, so. I think we'll see if we can close the door officially. But here's an example. Okay. out of 365 days, 72 of them were untreated. Yeah? I don't know. I'm we don't really have a rival city. We should just make it the rival city, right? Clash. Out of 365 days, what, 10? No, let's do 72. 72 days were untreated. Okay. Now I need to do a little bit of sleuthing to find what that proportion is.
72 over 365.
Is yeah 19.726%. Now let's say we're concerned if it's more than 15% in this rival city. I don't know. And so yeah, it was going to be about payday loans, so this is better, I think, even though it's wonky. We're concerned if more than 15% of days are untreated. Okay. Now, 72 out of 365 is more than 15%. But what we want to establish is if it's significantly more than 15%, right? Taking into account the spread and things like that. Okay. And so should we be concerned? So this is what we call a one sample proportion type of question. Okay? And I'm going to be harping on these types of questions because that's a critical step in your analysis, is to figure out, okay, well, what type of data do I have, right? Things like, okay, so I just have one sample and it has to be categorical, right? And I need to have some success that I can measure, right? A success in this case is the untreated days, right? That's the thing that I'm concerned about, okay? And so our p hat, our sample proportion, okay, our p hat generically is going to be x over n, the number of successes over the total sample size. So in this case, 72 over 365, which we're going to convert to a decimal, 0.197260274, or roughly, because I won't make you lug all those around, let's keep 3 decimal places. Ideally, you keep all of them, but I know you guys are averse. And it makes it nicer for our calculations. Okay. So now, our sample proportion is 19.7%, right? And like we said, that is higher than 15%, but we want to establish if it's significantly higher. Now, what we're going to rely on is called the central limit theorem, which I know a lot of you worked on, that assignment that I posted last day, right? And to kind of show you the central limit theorem in action. And I figured out what the problem was, but it's okay. Now, the central limit theorem for proportions says that p hat, okay, because we understand that, okay, this was just 365 days, and like I said, it's a little bit wonky, but it's okay. But the distribution of all the years, let's say, is going to follow a normal distribution. Hey, what the heck? We were just working on that, right? Z-scores, right, come from a normal distribution. And so that's great, right? We know how a normal distribution behaves. And wow, it's almost like I planned it like this. It's gonna have a mean of P. That's the population proportion. Okay? And so it's gonna be centered on P, okay? And maybe for today, usually I don't write the mu equals P, but just for our first one, right? And then we had a sigma. Now, something is going to just change slightly, but sigma is going to be PQ over N. And what is Q? Where Q is just shorthand for 1 minus P, okay? Because I'm lazy. I don't want to write 1 minus P. Just want to write a Q. And it's pretty standard to use Q. But if you want to write 1 minus P, go for it. Think of all those extra keystrokes if you're typing. Yikes. Right. The square root of P, which is the population proportion of successes, right, times the population proportion of failures, right? That would be 1 minus P, divided by your sample size. Now this is called your standard error, okay? And that's only because if we call it sigma, well, sigma is the standard deviation, but now I have a standard deviation of a distribution of sample statistics. And so it gets a little boggy. And so we rename this. Instead of sigma, we call this the standard error And I'll say this, your quizzes are marked, but let's grab them after class. I know, it's so exciting. Instead of sigma, we call this the standard error of p hat. So p hat is going to have some spread, right? And if you've done that exercise I posted, then you were able to generate a bunch of p hats, 100 of them, right? And you were able to make a histogram of them, and you saw that they were centered on p with a spread that was roughly the same as the square root of pq over n. Right? And so that's nice. From here on out, we don't need to, go through the motions. If I tell you that there's a central limit theorem, and there will be for other distributions as well, right? Then you're just hopefully able to kind of, okay, great. Then I can use the normal distribution. Okay. So this normal distribution, right? Knowing it follows it follows the normal distribution or a normal distribution. Lets us use z-scores to calculate probabilities, right? Lets us use z-scores to calculate probabilities. I will say this, I am gonna kind of stick to only a portion of the chapters. We're gonna stick to the mathematical models just because the randomization techniques and the bootstrapping that we introduced before, I might sprinkle them in just to kind of link the two. But in terms of what I can test you on, it's really just the mathematical models, right? And so, because you don't have a computer in the quiz. You do in life though, but that's okay. Another reason is in industry, it's the mathematical models that you would be expected to know and be able to run, okay? We're just not there yet. Okay, so what does this tell us? Well, it tells us the shape. Looks like this, right? This is my distribution of p hats. We had a sample of 365 days, right? And we found some proportion of those days to be untreated. And so now what the central limit theorem says is this is going to be centered on p. Okay? So this is going to be centered on p. Okay? And I'll make that bigger. And the standard error of p hat, usually we denote a SE and then subscript p hat, because there's going to be a standard error for all our point estimates. And so this is our first one, but it's good to get in the habit, is generally PQ over N. Okay. Now, the problem is we don't know what P is, right? And that means we don't know what Q is. We know what N is, right? That's our sample size. Okay? And so here we run into some troubles because we don't know what P and Q are. Okay? And usually we spend some time kind of talking about why it is, but we only have the one day and not, 3 days. I know, I guess I could make it whatever I want. So the standard error of p hat is PQ over N. We don't know what P is, right? We don't know what P is. So depending on if we're going to make a confidence interval or a hypothesis test, right, that's going to determine what our best guess for P is. Yeah. And so, and I should say, so we use our best guess for P. If we're building a confidence interval, then our best guess for P is going to be P hat, right? Why not? I have my sample proportion and I assume that if I collected it randomly and it's representative of the population, there's no reason to think that it would be a bad representative of P, okay? And so for a confidence interval, our best guess for P is P hat, the sample proportion. So then the standard error of P hat is the square root of P hat Q hat over N. Any guesses on what Q hat could be? 1 minus P hat. This one? Yeah, that's a P hat, but it looks like a B hat. A confidence interval, remember we build our confidence interval around our best guess, right? For the parameter that we're interested in. Yeah. And so, let's see here. Any confidence interval is going to have a point estimate plus minus, I'll use Z star for now. It's going to be replaced by a critical value, right? But we've seen this Z star before. I'll even say recall, even though we have seen it, right? But if you don't remember, it's okay. Oops. Times the standard error of the point estimate. Right. So you take your point estimate, which in this case, right, your point estimate is always kind of your best guess. It's from your sample, and so it's going to be your P hat if you're trying to capture a population proportion. Right? We're trying to use the sample to learn about what the population might be. Plus minus Z star times the square root of P hat Q hat over N. And we saw it briefly, but this whole chunk, right, the standard error, moving out as many standard errors, right, as your Z tells you to, that depends on what confidence level you want, right? And so, right, if I want a 95% confidence interval, I need to move out 1.96 standard errors now instead of standard deviations, because the standard errors are kind of replacing them. Yeah. And so now this whole, I call it a buffer, is called the margin of error. Right. Plus a little down, yeah, down a little, up a little. Right. And then we've made a confidence interval. I saved room on this side. If we're doing a hypothesis test, then we replace our best guess for P with the hypothesized value. Okay. I've got some idea of what I want to compare my sample proportion to, right? And so just generically, we call that P naught, right? Because it's from our null hypothesis. Okay, and so for a hypothesis test, our best guess for P is the hypothesized value so in your null hypothesis, we're hypothesizing about the whole population, right? And so for a one sample proportion type of question, we're hypothesizing about P. Right? And how it compares to some P naught. Okay? Where this P naught, and I'll make a note here, where P naught is the value we want to compare P hat to. So in our made up example, right? We had a sample proportion of 0.197, but really what we're trying to establish here, way back here, we're concerned if more than 15% of days. Now 15% is 0.15 as a proportion, right? And so this would be the value that I'm going to compare my sample proportion to. Yeah. So I'll do the general one here. Yeah. And then we'll jump into the example. Now Z, in general, okay, we've seen Z like this. Z is X minus mu over sigma. Okay. But in general, right, Z, we're going to be able to calculate as a point estimate, how far is it from the hypothesized value? Okay. And then taking into account the spread, the standard error. Okay. And so it's got the same behavior, but now Z is going to be a point estimate minus the null value, right, or the hypothesized value, if you will, divided by the standard error of the point estimate. Right? How far is my p hat, right? That's my point estimate. So in this case, Z is going to be p hat, that's my point estimate, minus p naught, right? My hypothesized value. How far is it from 0.15? Taking into account our standard error of the point estimate, but now that I have this hypothesized value, then we're better off using this because my hypothesis says that P is P naught, right? And so there's no reason to use P hat anymore, right? And so then we assume that it is P naught until we have evidence against it. Yeah. So then our standard error becomes P naught Q naught over N square rooted. Q naught being 1 minus P naught. Slightly more mature version of Z, right? But what's really nice is, okay, once I have this Z behaves the same way always, right? So once I have a Z, no matter how complicated it was to get there, right, Z is going to behave the same, and we can use the norm.s.dist command in Excel to find areas under the curve. I know, I thought we were done with that. No way, we're just getting started. So what's going to happen is in our hypothesis test especially, we're going to be centered on P naught. Yeah? Because my null hypothesis, I have to assume that P is equal to P naught, right? Because that was my null hypothesis here. Okay. I've held off on the alternative for a little bit. Right. That'll depend on the question. I still need to talk about P and how it compares to P naught, but whether I use a less than, a greater than, or a not equal to, right, that's going to depend on the question. So now I have a P hat that I know is above P naught, right? And just to visualize it, I'll stick it there. Right? Why not? Our Z is going to tell us how many standard errors we are away from this P naught. Okay. There's a realm here, kind of this area, right? There's just kind of thresholds, right? But there's a realm there where we say, close enough to P naught, right? No cause for concern. This was just a sample, and so I don't expect it to be bang on, right? There's some wiggle room there, okay? But then we hit a threshold that we don't know where it is yet, right? And what we use instead is we say, okay, let's use a p-value, mostly because a formal hypothesis testing framework still uses a p-value. Okay? So what is the p-value? This area is the one-sided p-value if we're above the center, right? If we're above P naught, then the p-value is going to be, remember, p-value is the probability of seeing something as extreme or more extreme, right? So it's always going to be the area in the tail, right? And if you had a two-sided test, what would you do? You would multiply this by 2. You would say, okay, I'd be just as concerned if it was on the lower end, right? In our scenario, right, we're only concerned if it's higher than 0.15, right? And so then this is the only p-value that I am interested in. So let's see here. I guess I should mention, because this is kind of a leap, that it follows a normal distribution, right? A categorical variable follows a normal distribution. I know, but it's true. As long as some conditions are met. And broad strokes, our observations have to be independent of each other, right? How can we accomplish that? We can accomplish that by randomly sampling, right? We collect a random sample. Okay? And so out of 365 randomly sampled days, let's add that in, whatever. Could have been 300 or something, but we'll keep it where it was. And so to get this normal distribution, one of the things that we need to ensure is that we have independent observations. Otherwise, it's not going to follow a normal distribution. But another thing is that we need to have a large enough sample size. And so I don't want to talk about the assumptions here, but I will post a summary, and you know that you need to check the assumptions, because and maybe if there's time at the end, then I'll sneak them in. Okay? But they're a lot of work, and they're not something that I'm expecting on a quiz or the final exam, right? More of an assignment type of deal. Okay? But I guess I should. Okay, fine, you got me. In order for the CLT, which I'm not sure I mentioned, but it's called the central limit theorem. And I know I've mentioned it before, but in order for the central limit theorem to apply, some conditions must be satisfied. One, independence. Independence. By randomly sampling, right, properly, right, we can assume that observations are independent of each other. So by randomly sampling, we can assume observations are independent of each other. If you haven't randomly sampled, what do you have to say? You have to say, I assume my observations are independent of each other, right? Or if it doesn't say, like I forgot to say, right, then we have to assume that those observations are independent of each other. The second condition is often called the sample size condition, but I like to call it the normality condition because it's the reason we're able to assume normality. Okay. And so the sample size condition depends on if we're doing a confidence interval or a hypothesis test. Oh, I know. For a confidence interval, we need at least 10 observed successes, failures. Wait, no. We need at least 10 observed successes and at least 10 observed failures. Making our smallest possible sample size what? 20, right? And that's assuming a perfect 50-50 split, right? If you're trying to detect something that's really, really rare, right, then you need to up your sample size so that you can actually see it in your sample reasonably, right? And so that's what this condition says, okay? And how do we check it? We check it by X is the number of successes, right? And I'm going to highlight the observed successes for a confidence interval. X, which if you don't have the exact number of successes, maybe I only gave you a sample size and a sample proportion, okay, then you can calculate it by taking n times p hat, right? Since p hat is x over n. But usually I'll just give you the number of successes. And if you have a data set, you would have the number of successes. Right? And this has to be greater than or equal to 10, right? Is how we check that mathematically. If x out of n are successes, then n minus x must be failures. They're not a success, they're a failure. And so then I have n times q hat has to be greater than or equal to 10. Okay. Like I said, this is not something that I'm going to test you on because it is pretty boggy stuff. But if you're writing a report, then you do have to have it somewhere in an appendix somewhere, usually kind of shove it in the back. I did it. See, I'm allowed to do what I'm doing. Notice the, this matches the standard error, right? So here, in a confidence interval, right, we use p hat, q hat in our standard error. So if we're doing a hypothesis test, yes, we are going to use p naught, q naught instead, right? And so that's the only change. Oops. If we're doing a hypothesis test, oops. We need at least skip some words here. We need at least 10 expected successes. Expected under H naught. So usually I don't say that part, but that's implied, right? So my expected successes is what would I expect to see if H naught was true? And so, and at least 10 expected failures. Right, the difference being the expected. We can calculate that. Right? The math is going to look like this. N times P naught. Right? That's going to be my expected number of successes if H naught is true. Okay? Has to be greater than or equal to 10. And similarly, N times Q naught has to be greater than or equal to 10. If my N's, right, all satisfy these conditions, then I can go ahead and assume the normal distribution, and I can leverage the Z scores, right, and kind of and use Excel to find areas under the curve. If these conditions are not satisfied, you would have to use a randomization technique or a bootstrap. And so, but these are the conditions. You have to check independence and the sample size condition. But on the quiz and on the final exam, I'll say, you may assume the conditions for inference are satisfied. And then you can bypass all that. Right? But now you know you have to do it. And it's tedious, but pretty fun once you get the hang of it. So here as a little note, if these conditions are not satisfied, satisfied, we can use randomization or bootstrapping instead. So that's nice. So you're not, completely pooped if these conditions aren't met, right? There are instances where I can imagine you can't get that many samples, right? Either very expensive or whatever. I thought of a silly categorical variable. The number of times that you go out on the water and you see a Ogopogo, you need to have a pretty big sample size. Okay, so in order to assume normality, you're gonna go for 0. Oh, there's a chance. Okay. I think we're ready. Let's start with a hypothesis test because it's the most important. And you know what? I'm going to scratch this. Keep it nice and fresh. So now we're ready to do this sample. If you're trying to establish if you are concerned or not, right, then you're comparing your sample proportion to 15%. Okay? And so what we need to do is we need to do a hypothesis test. Okay? And a hypothesis test is always going to have, I break it down into 4 steps. Okay? And so, but you can break it down. I've seen it broken down into like 9 steps, which is crazy because how can you possibly remember it? But when it says things like, should we be concerned? Or is there evidence that blah, 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 blah? Okay. Any sort of terminology like that means you're going to have to do a hypothesis test. Okay. So step 1 of a hypothesis test is to state the hypotheses. We've had some practice. Right? I'm so pleased you did so well on the quiz. Right? But your null hypothesis, we have to assume that P is 0.15 in this case until we have proof otherwise, right? Until we have evidence against it. So for us, the null hypothesis, I want to compare my sample proportion, 72 out of 365, I want to compare it to 0.15. So then my null hypothesis is that P is equal to 0.15. A key part of hypothesis testing is that we do all our testing assuming H0 is true until we have proof otherwise. Okay. And so leads us to our alternative hypothesis. Has to be about the population, right? We know everything we need to know about P hat and our entire sample, right? That's not interesting to us. We're trying to learn about the population proportion P. And so P, how does it compare to 0.15? Right? You don't want to switch up what you're comparing it to, right? Halfway through. And so in our case, right, we want this to reflect when we would be concerned. Right? And so we're concerned if more than 15% of days are untreated. And so to reflect that, I have a greater than here. This makes it a one-sided test, right? I'm only concerned with one extreme. Okay? And so if you made it two-sided, that would be safe, right? Makes it harder to reject H0 when you shouldn't, right? And so that's safe. So as a default, you can have a two-sided test, so a not equal to there, but the calculations are just slightly simpler if we do a one-sided. So let's do that for now. But this is a one-sided test. I only care about the one extreme. Step 1, state your hypotheses. Done. All right. Now, step 2, and you'll notice these steps are very generic, right? And that's because they're going to be true for any hypothesis test. Is going to be, I call it do the test. This makes me think of do the do, but more boring. Calculate the test statistic. Now the test statistic is that Z score in this case, right? How far, how many standard errors is my P hat from my P naught, right? So that's going to be my test statistic. Z is P hat minus P naught over the square root of P naught Q naught over N. Any test statistic will have this format of my point estimate How far is it from my null value, taking into account the spread of my point estimate? My goal is to get you to a point where you maybe don't have the exact tools that you need to do a hypothesis test, but you're able to kind of Google your way to, okay, what kind of a hypothesis test would I need if my data looks like this, right? And you can't make it match anything that we've done in class, right? Because we're only going to do a limited amount, okay? And so then my goal is for you to be able to Google it, and all you really need is, well, what do my hypotheses look like? And how do I calculate my test statistic? After that, you're back to where we have been for the past couple of weeks, I would say, right? Finding the area in the tail and the p-value, and it depends on the distribution of the test statistic, right? So far, we're looking at a Z, but there are others, right? There are many others. Okay, but they all behave the same, because then when you find the p-value, it's really just the probability of seeing something more extreme, right? The area in the tail. Okay. And we're going to quickly graduate to a chi-squared, right? Chi-squared test statistic, right? And so then, but we still find the area in the tail, right? So that's my goal. All you'll need is, okay, well, what do my hypotheses look like? How do I calculate my test statistic? And then you're off to the races. Okay? Because then you'll have Excel to do the rest. So in our case, we had a p-hat of, what did we say, 72 over 365, which we rounded to 0.197. It's my best guess at what the population proportion looks like from my sample. And this might be just insane, but we'll see. How far is it from 0.15? Taking into account the spread, which is going to be P naught Q naught. Now P naught is 0.15, which means Q naught is 1 minus 0.15 divided by N, which is 365. .047 divided by 0.15, oops, 1 minus 0.15 times 0.15 divided by my standard error, unless I flubbed it, 0.01868999724. And of course, in Excel, you would keep all your decimal places, or you would be able to. So 0. Oh, phew. I was getting worried. I was worried my Z was going to be like 20 or something. But it's a very reasonable 2.514717464, or roughly 2.5. I don't know, let's just go for 1.5. From the quiz, what does that tell you? What? This was on the quiz, but we're just learning it now. I know, but what does a Z-score tell you? It tells you that 0.197 is 2.515 standard errors above 0.15. right? Quite far, right? Kind of within reason, right? But what does this look like? If we're on a normal distribution centered on 0, right? Z is centered on 0. And we found that Z is equal to 2.515. Then as long as we remember that the p-value is the probability of seeing something as extreme or more extreme, right? But it should also match your alternative hypothesis, right? So here, if we go back to our alternative hypothesis, if I want to prove that p is greater than 0.15, right, then I want to find the area in the upper tail. Okay? If I want to prove that it's less than 0.15, well, it's going to be hard to use 19 to prove that it's less than 15, right? So you shouldn't do that. You could use it to prove that it's not equal to 0.15, right? By replicating it in the other tail. So for us, this is going to be our one-sided p-value. So we use our Z, right? And that's going to help us calculate our p-value, which is step 3. Step 3 of a hypothesis test. Find the p-value. We're going to use Excel, and I don't have it fired up yet. I'll just grab a, oh, whoops. I probably shouldn't work in a shared spreadsheet with the department. We're like, oh, what were you doing here? All right. Try to zoom in here. Norm.s.dist gives me the area to the left, right? I feed it a z-score, it gives me the area to the left, that's okay. And so here I have equals norm.s.dist, and you can use your calculator if you prefer, but we had 2.515, and this cumulative for normal distributions is always true. Oh, there. Don't want those brackets. Wait, 994048. Okay. So
That's left side.
that's the left side. Yeah, exactly. But to what the heck? That's weird. Oh, any update makes me feel so old. You can't do that to me. This is, like we said, the area to the left, 2.515, and we find that this area is 0.994048. Oh. Oh, thanks. Okay. Making this area, right, 1 minus 0.994048. Scientific notation, 0, 0, 5, 9, 5, 2, 1, 2, 3. Okay. So now I have my p-value. Okay. And now from quiz 3, right? You know that I'll put it right on the front page, anything that you need, right? And so you don't need to be able to use your calculator, but it might be nice to just get comfortable with using your calculator. Okay. But values are all the same. Okay. So this is my p-value. This is my one-sided p-value. Very, very small. And so now what do we do? Step 4 is our conclusion. Now our conclusion will always have 3 parts. And so that's why I say, okay, hypothesis testing, you can break it down into, I don't know, 7 parts or something reasonable, but I like 4 kind of distinct chunks. You don't have to list the steps, but you do have to do all the steps. So you may as well, I find that it's helpful to have kind of a framework, right, to work off of. But if you don't like it, that's fine. You still have to do all the things. So, but you don't have to list them all. Okay. Now, our conclusion is if the p-value is less than the alpha level, right, or generically small enough, right, then we have enough evidence to reject H naught. Okay? And if we're rejecting H naught, it's in favor of HA. So what does that mean? It means that for some area here, right, for kind of some region here, we fail to reject H naught. Right? It's basically at P, right? And so here we fail to reject H naught. But then we reach some threshold where we've moved too many standard errors away to consider them the same, right? There's a p-value chance that we're wrong, right? And so we could be wrong in our decision, but this is small enough, right, for us to feel comfortable saying, I don't think that the null hypothesis that P is 0.15 is reasonable anymore. Another way that you can think of the p-value is as the probability that the null hypothesis is true. Right? If that's small, then you start to think, oh, actually, no. Now, I will warn that there are kind of technical reasons why that's not the definition, but it is a helpful way of thinking about the p-value. Right? And so for our purposes, good enough. Right? If it helps you to think about, I will say this, I'll put it down here. We can think of the p-value as the probability that H naught is true. We did all our testing assuming that H naught was true, right? And so we can think of the p-value as this probability, if it helps. If it doesn't, that's okay. But our conclusion, right? Our conclusion in general is if the p-value is small enough, and we've already seen that, okay, small enough means less than alpha, some preset alpha level. We also saw that alpha is the predetermined type 1 error rate that we're okay with having, right? And so if the p-value is small enough, so less than alpha, we have enough evidence to reject H naught. Okay, I gotta find it. I have to find it. Please stay on the line. Hey, where was it? Okay. Huh. It's a little cheeky, but it is helpful. And the number of times that I've seen, if the P is low, then the null hypothesis must go in the margins of a final exam. I can't stop. I should probably stop using it, but I do think it's helpful, right? And so if the P is low, then the null hypothesis must go. Snoop. So what he's actually saying is if the p-value is small enough, less than the alpha level, right, then we have enough evidence to reject H naught. Right? But this is catchier, I think. Right? But that is what it's saying. And so, and because this concept is just a very difficult concept for a lot of students, right? I can't not bring something in that makes it easier. So one important thing here is that our conclusion has to be in terms of the null hypothesis. Okay, you completely parking lot the alternative hypothesis, right? It's just kind of if you reject H naught, then you can say, you can offer up the alternative, okay? But you either have enough evidence to reject H naught or you do not have enough evidence to reject H naught, okay? And that's because you did all your testing assuming H naught was true, right? And then we can draw our conclusions from that. Okay. Our conclusion must be about H naught, since we did all our testing assuming H naught was true. And I was marking your quizzes last night, and I didn't write it every time I saw it, but if you flip to your the last page, right, the type 1, type 2 errors, if you were talking about the alternative hypothesis, right, then you're going to need to reframe that. I didn't, you know, unless it didn't make sense, I didn't take any marks off. I kind of got there, right? But you always want to be talking about your H naught, your null hypothesis. And your quizzes are here, but you can grab them after class. Oh my gosh. Up 2. So our conclusion, like I said, has 3 parts. Okay. You're going to compare the p-value to the alpha level, right? It either is less than the alpha level or it is not less than the alpha level, okay? And I don't want you, as we're just starting, right? Those are your only 2 options, right? I don't want you to throw in a greater than or anything like that because it messes with the symmetry, okay? But also it can get confusing, okay? And so our conclusion Our conclusion has 3 parts. Maybe I'll do this in blue, and then I'll do part 1. Compare the p-value to the alpha level. Compare the p-value to the alpha level. Then you're going to state your conclusion in terms of H naught, right? You either have enough evidence to reject H naught or you do not have enough evidence to reject H naught. So then you state your conclusion. Wow, I'm missing. Conclusion in terms of H naught. And then finally, the one people love to forget to do. Conclusion in terms of the question, right? You set out to answer this question, but at this point, you've done a ton of work, right? And so a lot of I see it so many times where you just forget to answer the question. I reject H naught. Done. Conclusion in terms of the question, right? What does rejecting H naught or failing to reject H naught mean to your boss, for example? All right. So really the only part that they're going to be reading. So you don't want to forget it. So for us, I'll put it conclusion. It's going to look like this. I'll have to remind myself it was very small, 0.005952. Since our one-sided p-value, right? This is where you get to showcase all the things that you know, right? You're not incorporating anything new, you're just stating it all as a conclusion. So since our one-sided p-value of 0.005, let's see here, 952 is less than our, now I'm going to assume it's 0.05, right? That's our default alpha level. Is less than our alpha level of 0.05, right? Don't let those zeros throw you. It is less than. So it is less than our alpha level, so it is small enough, right? Oh, you know what? Let me match I'll match the color scheme. There. There you've compared the p-value to the alpha level. That's what that looks like. So it is less than our alpha level at 0.05, which means we have enough evidence to reject H naught. Now, if you're rejecting H naught, you can say in favor of HA, or if you just want to kind of leave it there, that's okay, right? Because I don't want you to get boggy with the HA, right? It has to be in terms of H naught. I'll add it in for completeness in favor of HA. Therefore, the proportion of untreated days is significantly higher than 0.15 or 15%. This is where you just rephrase the question as an answer. Now, I think I asked, should we be concerned? Yes, we should be concerned. Right? So yes, therefore, we should be concerned as the proportion of untreated days is significantly higher than 0.15 or 15%. Significantly because our p-value is small enough. Right? 0.197 is higher than 15, right? But here, the whole point of hypothesis testing is this significantly higher. Right? Let's say, just to see what this would look like, right? I'm going to copy and paste this entire thing. Assume the p-value was 0.156 instead. Right. Your Z was close, right? So let's say a Z of 1.2 or something like that. You didn't move very far from your hypothesized proportion. And so assume that the p-value, now I'm making it bigger than 0.05, right? Just to see the symmetry. So since our one-sided p-value of 0.156, let's say, is not less than our alpha level of 0.05, we do not have enough evidence to reject H0. If you're not rejecting it, you can stop there. Therefore, we should not be concerned as the proportion of untreated days is not significantly higher than 0.15. Right? And so that's why I want you to, right, our p-value, it either is less than the alpha level or it is not less than the alpha level, because then you get this symmetry where you can just throw in some knots everywhere. Right? Nice. Okay. So if it's not 0.15, what would a follow-up question be? Well, okay, so it's greater than 0.15. Well, what is it? Right? And so how bad is it? That's where a confidence interval comes in. So to determine a plausible range of proportions, or range for the population proportion, we can construct a confidence interval, right? Because that gives us, okay, so it's higher than 15%. That's okay, great, or bad, I guess. But now we want to know, okay, well then what is it, right? Based off of your sample, what do you think it could reasonably be, right? And so that's where we can, to determine a plausible range for the population proportion, we can construct a confidence interval. So a question might read something like this. Construct a 95% confidence interval for the proportion of untreated days. I'll throw in the true proportion of untreated days. It's asking for a confidence interval, right? Then you need to snag the formula, which is going to always be a point estimate plus minus the margin of error, right? Which is going to be your critical value times your standard error, right? And so it's going to be plus minus Z star times the square root. And here, because I don't have a hypothesized value for my confidence interval, right? We did have one, but for confidence intervals, we just use our p hat instead over n. Recall Z star is 1.96 for a 95% confidence interval. We spent a lot of time kind of getting there. And so from here on out, I'll just give you the Z stars for the common confidence levels. Okay. Our p hat was 0.197. And then I have to move out 1.96 standard errors to capture the central 95% of the curve, right? I do expect you to be able to find this Z star, but we're kind of over it. 1.96 times, and p hat is 0.197 times 1 minus 0.197 divided by our n, which is 365. Times 0.197 divided by 365, square root that. The standard error that I get, and this is mostly so you can compare your values, 0.0208182621. That's my standard error. Once I multiply it by 1.96, that's going to be my margin of error. And so times 1.96, I get 0.197 plus minus 0.040803799198. This is called our margin of error. Right? And a lot of articles, if you're reading kind of academic journals and things like that, will just report the margin of error. So now I take 0.197 and I subtract this for my lower bound, and then I add for my upper bound. And I get an interval of 0.197 minus that guy. Hey, syntax error. Minus, oh. Sold. I get 0.156196208 up to 0.197 plus that guy. 0.237803792. We can round this to 3 decimal places, let's say. It depends on, you know, how how picky you want to be, right? Or maybe how precise your measurements are and things like that. Or somewhere between 0.156 to 0.238. This gives you a plausible range where your population proportion could reasonably be, right? And so now we need to interpret this confidence interval, right? And we use that same standard blurb that we've seen just briefly before, but we say we are 95% confident the interval from 0.156, or if you prefer percentages, 15.6%, right? But I'll just keep the proportions. 0.156 to 0.238 captures, and then you just snag whatever the wording was, construct a 95% confidence interval for the true proportion of untreated days. Right? And so we're 95% confident that this interval captures the true proportion of untreated days. It's just above 15, right? Which matches what we found in our Z, but also our p-value, right? It wasn't, off the charts, but here we're saying, okay, on a number line, if I have my proportion is between 0 and 1, I'm saying I'm 95% confident that it's somewhere here between 0.156 and 0.238. Not to scale, but our hypothesized value, right, of 0.15 is outside this interval, right? And so where the field is heading is just using a confidence interval instead of the p-values. But I suspect because industry tends to take a long time to relearn things, so they'll be using p-values still. And so that's why it's really important that we have a good handle on the p-values. But you can just build a confidence interval and see if your hypothesized value is in this interval or not, right? And that would be the same. You would reach the same conclusion, right? I'm 95% confident that 0.15 is not in the interval, right? Or is not one of the population proportions, right? And so we can use this confidence interval to do a hypothesis test, right? Which is what we've developed. On the quiz, you did that, right? Was there evidence that a majority, blah, 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 right? Was 50% in there or out of it? Okay. So we've already done that. Wow. Just wow. And I'm remembering I was going to do the assumptions, but we already did the assumptions. Wow. That is great. Tuesday, we'll look at comparing proportions. So let's say we have Lake 1 and Lake 2 or something like that. I'll try to pick Allison's brain about some reasonable categorical data. If you have any questions, let me know. Otherwise, enjoy your weekend. Come grab your quiz if you don't have it. Catch you on the flip side. Bye, Sabrina.